Tomahawk missiles, kamikaze drones, and a daring counterattack turned what seemed like the end of a battle into an explosion of conflict like never before. What's really going on? This video is solely for technology analysis. It does not promote any conflict or violence. Military operations on the morning of March 16th. In the early hours of March 16th, just after midnight, US forces launched a series of follow-up actions as part of the Operational Space Control campaign. This time, the target was positions not fully addressed in the initial phase, focusing on logistical support facilities and drone transfer hubs. During this deployment, two Arleigh Burke-class destroyers, the USS Stout and the USS Jason Dunham, activated their Tomahawk cruise missile systems. These weapons fly at low altitudes, navigate precisely using digital terrain mapping, and are often chosen in situations demanding accurate strikes that minimize risks to ground forces and civilians in the area. The facility targeted in this strike was believed to be a key logistical hub where the adversary could deploy small boats and unmanned surface vehicles, USVs. Disabling this area was seen as a tactical blow to the enemy's mobility and a move to reshape the maritime battlefield dynamics in the near future. From a defense technology perspective, this operation demonstrated the trend of integrating smart weapons into flexible response strategies, emphasizing precision, speed, and effective damage control in modern conflict environments. It's a prime example of using advanced technology to boost mission performance while maintaining necessary restraint amid complex hostilities. The B-1 strike from the Turkish base. At 4:15 a.m., B-1B Lancer strategic bombers, launched from a base in Turkey, carried out a long-range missile deployment against pre-identified critical enemy positions. This was part of a layered combat strategy, combining long-range strikes and precision attacks to disable enemy command control capabilities and battlefield logistics systems. The B-1Bs were equipped with AGM-158 JASSM Joint Air-to-Surface Standoff Missiles, long-range weapons designed for operation in heavily defended environments. JASSM uses an inertial navigation system combined with GPS guidance and features a penetrator warhead, making it effective against hardened or semi-hardened targets like underground command centers or ammunition depots. This deployment took place when the Houthis' air defense systems were reportedly disrupted by earlier operations. This made their air defense assets, such as automatic cannons, short-range missiles, and early warning radars, far less effective, especially against radar-evading weapons like JASSM. Moreover, the B-1B's ability to launch missiles from standoff range illustrates modern thinking in airstrike strategy. Rather than conducting direct bomb runs, priority is given to keeping aircraft at a safe distance, using smart weapons to enhance target destruction while minimizing risk. From a defense tech angle, this is a classic example of integrating traditional combat platforms with new generation weapons, extending the relevance of decades-old aircraft in US air power. JASSM is not only a precision strike tool, but also a key part of strategic deterrence, allowing air forces to retain superiority in asymmetric and high-threat combat zones. Finally, this airstrike played a role in disrupting the enemy's response and logistics cycle, paving the way for other units to approach target areas with minimal resistance, an essential part of the modern overall campaign structure. From a personal strategic perspective, I believe the B-1B strike was not merely a calculated military move, but a clear demonstration of the United States' layered combat capabilities and the flexibility of its air power deployment. Leveraging long-range superiority through a combination of smart weaponry and decades-old flight platforms is a testament to modern military thinking. It's not only about acquiring new technologies, but about maximizing the effectiveness of existing assets, striking a balance between modernization and real-world combat efficiency. F-35C and the bombing of the weapons depot. Immediately after the B-1 bomber formation completed its mission and withdrew safely from the combat zone, F-35C stealth fighters from the USS Harry S. Truman Carrier Strike Group were deployed for the next phase of the operation. The designated targets were two weapons storage facilities in the Marie Gouvernay area, believed to play a central role in the adversary's strategic logistics chain. A notable aspect of this mission was the absence of air defense response from local forces, which may reflect a strategy of resource preservation or a a reallocation of defensive assets for longer-term strategic scenarios. From a military analysis perspective, this indicates that priority levels among the warring parties are being adjusted based on intensity and location of combat. The F-35C, with its stealth capabilities and multi-directional sensor integration, is a modern aviation platform designed to enhance access and combat effectiveness in heavily defended environments while minimizing electromagnetic radiation traces to avoid early detection. The deployment of this aircraft at this campaign stage represents a strategy that blends precision strike capabilities with high survivability in high-tech conflict environments. From a defense technology standpoint, this mission is a prime example of the trend to modernize air forces to optimize performance in asymmetric environments, while applying coordinated operations across ground, sea, and air platforms to ensure connectivity and timely response throughout the campaign. The Houthis counterstrike the attack on USS Gettysburg. Around noon, the AN/SPY-1 multifunction radar aboard the Ticonderoga-class cruiser USS Gettysburg detected multiple signals indicating a large-scale approach underway. This was a vastly different scenario from the previous skirmishes, which only involved small-scale attacks. This time, the Houthis deployed a large volume of aerial weapons simultaneously, seemingly focusing all firepower on a single target to test and overwhelm the ship's defense systems. Using saturation attack tactics is a classic asymmetric warfare method, often employed by forces lacking superior technology, but able to exploit numbers to pressure defense systems with limited processing capacity. The radar and fire control systems on Ticonderoga-class ships, though considered advanced, generally handle up to 12 to 18 targets simultaneously. When that number is exceeded, tactical response capabilities are stretched, and interception effectiveness can drop significantly. This situation was not only a test of the Aegis air defense system's technological capabilities, but also a strategic challenge for real-time command and risk management. Operational officers had to prioritize targets based on speed, approach angle, and potential threat level, a task requiring advanced calculation and instantaneous data analysis skills. Additionally, geographical and weather conditions played a crucial role during this phase. If the operation occurred in a narrow maritime area or under high signal interference, early detection and effective interception would become more complicated. This scenario shows that even well-equipped units can face challenges under constant pressure, especially without support from other platforms like surveillance UAVs, air defense frigates, or integrated high-altitude defense systems. From an academic and technological perspective, this scenario underscores the need to shift toward distributed interception systems, use AI in target prioritization, and integrate multi-platform sensor networks to ensure sustainability in modern combat, where asymmetry lies not in tech, but in deployment method and scale. This is a crucial lesson for all modern naval forces in the era of high-tech warfare. Smart interception tactics by the TAO and a bold decision. Facing a large number of simultaneous aerial targets, the Tactical Action Officer, TAO, and the ship's commanding officer made a tactically significant decision. Instead of following the traditional air defense rule of 2 missiles per target, to ensure the highest possible kill probability, they opted to allocate 1 SM-2 surface-to-air missile per target based on the assessment that the current system could achieve up to 90% interception effectiveness. This strategy not only demonstrated tactical adaptability under pressure, but also showed a deep understanding of the deployed weapon's actual performance. As a result, 6 out of 8 incoming missiles were successfully neutralized during the first wave of interception. The remaining 2 targets were handled by the close-in defense system using ESSM, Evolved Sea Sparrow missiles, typically deployed as a point defense measure, but in this case redefined as a proactive tactical solution in the ship's secondary defense layer, helping to maintain and reinforce the vessel's immediate safety zone. In addition, this situation unfolded under complex weather conditions and intense electronic interference, which challenged traditional sensor systems in accurately identifying the number and trajectories of incoming threats. Thanks to the ship's integrated fire control systems and automated target prioritization prioritization software, a key component of the Aegis combat system. The TAO was able to make rapid decisions based on fused data from multiple sensors, including the SPY-1 radar, infrared detection systems, and linked signals from escort vessels. This also highlights the importance of tactical training and modern war simulation environments using virtual reality, where officers are trained to handle high-speed, multi-directional, high-pressure scenarios, typical of modern electronic and asymmetric warfare. This situation clearly illustrates modern trends in high-tech warfare, combining real-time tactical decision-making with efficient utilization of all available defense layers, thus forming a flexible and high-performance multi-tiered defensive network. From a technological standpoint, this is a prime example of using defense systems as adaptive tactical tools in asymmetric conflict environments, where resource optimization and reaction speed become vital for survival. The counterstrike with the GBU-53 Stormbreaker. To counter highly mobile targets, such as enemy mobile command centers, the United States deployed the GBU-53/B Stormbreaker Smart Bomb, an advanced weapon system specifically designed to enhance combat effectiveness in environments with complex terrain, weather, and sensor conditions. Stormbreaker is equipped with a tri-mode seeker, infrared sensors to detect target heat signatures, millimeter wave radar to maintain tracking in low visibility conditions, and semi-active laser guidance for high accuracy in the terminal phase. By integrating 3 distinct sensing systems, this weapon can autonomously detect, track, and adjust its flight path to strike moving targets, regardless of poor weather or signal jamming. In this operation, Stormbreaker was used to strike lightweight command vehicles moving across complex terrain, including low mountain ranges and ruined urban zones. These targets could shift position continuously, hide in terrain, or operate beneath heavy radar interference. In such contexts, fixed navigation weapons would lack effectiveness, while Stormbreaker maximizes its capacity to self-locate and lock onto targets even while flying at medium-range speeds. Another noteworthy feature is the compatibility of the GBU-53 with multiple aircraft platforms such as the F-15E, FA-18, F-35, and B-1B, allowing U.S. forces to apply cross-platform tactics while increasing strike density on strategic targets. Additionally, each aircraft can carry a significant number of Stormbreakers due to its compact size, boosting firepower while maintaining maneuverability. The deployment of the GBU-53 reflects a growing trend in modern warfare, prioritizing weaponry with high adaptability and automation, suited to non-linear combat scenarios where rapidly changing environments and unpredictable target behaviors demand swift and precise responses from combat units. From a defense technology perspective, Stormbreaker represents a breakthrough in weapon systems capable of autonomous sensor data processing and tactical adaptation, helping to improve the overall performance of multi-layered combat networks in high-tech warfare settings. It is not merely a strike weapon, but a symbol of the shift from mechanical attack to smart warfare, where algorithms and sensor intelligence take center stage in modern conflict environments. In my view, the Stormbreaker represents more than just an evolution in precision strike capabilities. It embodies the future direction of warfare itself. As battlefield dynamics become increasingly unpredictable and decentralized, weapons like the GBU-53 offer a strategic edge, not only through their smart guidance, but by enabling real-time adaptation to complex conditions. It's a clear sign that the future of combat lies in systems that can think, sense, and act faster than human reaction time, redefining the rules of engagement in high-tech conflict zones. The Houthis' retaliatory drone attack. That same afternoon, radar aboard the USS Harry S. Truman aircraft carrier detected a large number of unmanned aerial vehicles, UAVs, rapidly approaching at varying altitudes and speeds. The UAV formation was dispersed, not flying in a uniform block, which made identification and tracking more difficult. This is a common tactic in swarm attacks, aiming to disrupt defense systems through sheer numbers and to confuse the naval force's assessment and reaction capabilities. Faced with limited missile defense resources aboard escort ships, where medium and short-range air defense systems experience high consumption rates, the strike group commander made a strategic decision to assign initial interception duties to the Naval Air Force, specifically FA-18 Super Hornet fighter jets. This move helped ease the burden on surface air defense systems while leveraging the mobility and rapid deployment of the fighter jets. The fighters were armed with AIM-120 AMRAAM medium-range air-to-air missiles, radar-guided weapons capable of autonomously homing in on targets in in high electronic interference conditions, and particularly effective against small, high-speed tactical UAVs. What stood out in this deployment was the coordination between aerial, surface, and unified tactical command sensors. Target data was shared through the Link 16 tactical network, allowing aircraft and warships to jointly detect, track, and destroy targets in real time. This clearly illustrates the principle of distributed lethality, a modern warfare concept emphasizing the ability to strike from multiple dispersed platforms unified by network technology and artificial intelligence. This event also highlights a growing trend in modern conflict environments: the use of UAVs as tools for strategic pressure, forcing opponents to deplete high-end resources in response to low-cost threats. This raises an urgent need to develop low-cost, rapid-response, highly automated air defense systems to counter the increasing use of UAV swarms in asymmetric warfare. From both defense technology and academic perspectives, this is a vivid example of the importance of interlinked platforms within a combat ecosystem, where every layer of weapons and sensors supports and reinforces the others, creating a deeply integrated and real-time responsive defense system. The 7-hour aerial battle. The aerial battle lasted over 7 consecutive hours between FA-18 Super Hornet fighters and a massive wave of UAVs, marking one of the tensest phases of the campaign. In this scenario, the UAV's objective was not limited to direct attacks, but also aimed to exert strategic attrition pressure on the carrier strike group's air and sea defense resources. This is a clear example of modern asymmetric warfare, where the attacking side uses low-cost, rapidly deployable devices that still degrade operational effectiveness and consume high-value defensive resources from the opponent. The prolonged nature of the air battle shows UAVs serve not only as physical weapons, but also as psychological warfare tools, forcing air defense forces to maintain high readiness for extended periods. At the core of the effective air defense in this battle was the IRST Block 2 sensor system, integrated into the FA-18 fighters. Unlike traditional radar, IRST is a passive detection system that uses thermal signals to track targets, allowing effective operation even when UAVs use stealth technology or fly at low altitudes in high electronic interference environments. Notably, IRST Block 2 can also analyze multiple targets and determine attack priority, helping pilots make quick, accurate decisions in dense combat environments. Its ability to operate continuously in daytime, nighttime, and adverse weather further reinforces its role in modern warfare, where the line between combat and surveillance is increasingly blurred. This engagement also highlights the need for a multi-layered air defense ecosystem, from active radar and passive sensors to high-response weapon platforms like AIM-120 and AIM-9X. Linking information between warships, fighter jets, and command control systems creates a unified combat environment. Sensor fusion, helping maintain air superiority throughout the prolonged engagement. From a strategic perspective, this air battle was not only a successful defensive operation, but also proof of the system's endurance, sustained combat performance, and optimized sensor technology under constant pressure, paving the way for more sustainable and long-term counter-UAV solutions in future high-tech warfare. After a grueling confrontation, U.S. Central Command realized the need to deliver a decisive blow to end the game. In the coming days, they plan to strike one final blow to bring down the Houthis, putting an end to the counterattack phase. This video is produced by Wild Eagle and is solely for technology analysis. It does not promote any conflict or violence.